Hi guys, so I just finished recording the alkene video, but I figured since I'm here, I might as well record the experiment 9 video real quick. The Fischer esterification between acetic acid and isopentyl alcohol to form isopentyl acetate using sulfuric acid. So this experiment is pretty cool. Let's see if I remember the whole procedure just from memory. So first off, you guys are you're doing an esterification reaction. So let me just show you what that looks like real quick. Share screen. Fischer esterification. It's the main way to form esters. You guys know what esters are. You can take an alcohol and carboxylic acid and combine them to form an ester. So right here, you have a carboxylic acid coming together with an alcohol. Here we have acetic acid with ethanol and O3H2SO4, sulfuric acid. And in this case, it forms your arbitrary ester with water byproduct. And in this case, forms ethyl acetate with water byproduct. So it's essentially a condensation reaction. Water is being evacuated and ester is condensing and forming. So let me just jump back, stop sharing. So first, you guys are going to take your 5 ml reaction vial, and you're going to, what you do is you pipette 800 microliters of your, I think it's isopentyl alcohol. I do, I have to double check the procedure again now. No, so it's the alcohol. So yep, you take your 5 ml reaction vial. You guys are going to take your blue silica beads. So these blue silica beads are a dehydrating agent. They just keep the reaction dry, because if water is able to get into the reaction, it will screw it up and it won't work properly. Because we know that water and acid come together to form pretty strong reagents that react with pi electrons and any reactive functional group, really to form different things. And carboxylic acids and alcohols are very reactive functional groups. So we don't want water to be in a reaction. And acetic acid is what? We know vinegar. So vinegar is 5% acetic acid, and the other 95 is just water. So acetic acid can take on water and likes to take on water. And vinegar has got a strong scent, and only 5% of that is acetic acid. So you guys will be using 95 to 100%, 95 to 99, I guess, percent acetic acid, which we call glacial acetic. Because when acetic acid is pure, it freezes at a pretty high temperature, around 16 degrees Celsius, and freezes into a solid block like a mini glacier. So anyways, you take 800 microliters, so a little bit less volume-wise of the isopentyl alcohol. You're going to add it, and then you're going to add it to your vial with the silica beads. Then to that, you're going to add an additional 1.5 milliliters, but this time of acetic acid. Now, once you have your acetic acid and your isopentyl alcohol in there, let's see here, total volume is now going to be 2.5 milliliters. Now you're going to add about 4 drops of your concentrated sulfuric acid. So that's provided, and sulfuric acid is pretty corrosive, so you want to be very careful with it. Make sure you add 4 drops, but don't add more and don't add less. 4 drops is perfect. Then you put that on reflux on a heat setting of 8 to 10, but it runs for about 1.5 hours, and then the workup takes a little while too. So this is actually one of the longer experiments that you would have run. It would have taken definitely the full 3 hours for some of you if we had run it in the actual lab today. But we're all online, so you guys don't have to deal with that. So anyways, it's on reflux, it's heating, it's running for 1.5 hours, and then when you guys take it off, you essentially just unscrew the vial once it's cooled down. And you are going to extract the liquid with a pipette. So you have your beads, they're sitting in a liquid, and your liquid is now your product, so you extract the liquid with a pipette, and then you wash the beads with some diethyl ether. So that's a solvent that's given. It's just 2 ethyl groups on either side of an oxygen, so diethyl ether. And it is highly volatile solvent. It boils away at about 26 degrees Celsius, which is pretty much room temperature. Room temperature is 22 to 25 degrees Celsius. It's 1 degree above the warmest room temperature. So it'll evaporate very quickly. So wash your silica beads with that to make sure you get all your product off the vial and off the beads and into your new test tube, which if I scroll down, we will see right here. And so Once you have all of your diethyl ether in your product in one test tube, you're going to add some water. And in this case, one of those times that you add water, the water wash is just to pull out the acid and the salt. Now that you've formed your ester, you can add water to extract byproducts and impurities. So in this case, you're also adding sodium bicarbonate to that water. So it's a sodium bicarbonate solution, not just water. And that's to neutralize any of the leftover acetic acid that's still in your solution that wasn't reacted. So if you have unreacted acetic acid left over, you don't want that to be there, because acids can break esters. Esters on drugs actually are the very first functional groups to break once they get in your body. That's part of something called pharmacokinetics. You guys will learn about your 4th or 5th year. I think 5th year maybe, but a PharmD. But yes, so when you take a certain drug, if there are any ester or amide groups in that drug, will be cleaved first, because it's very weak bond. It breaks with acid. And what do we know about the stomach and most of the interior of the human body? It's acidic. So a little fun fact there. So the sodium bicarbonate reacts with the acetic acid, as you can see where my mouse is here, to form sodium acetate, CO2, and water. So it'll bubble off CO2, form excess water, sodium acetate. Now, once you've shaken it up and let it vent, you're going to extract the top organic layer, the diethyl ether that has your product that's slightly yellow, and you're going to wash it again with water in another tube, and extract it again, the top organic layer. Now that organic layer needs to be dried because there's microscopic bits of water that are still in there that we can't see with our eyes. Remember, we've talked about this. So we have a pipette filled with granular sodium sulfate, a drying agent, and you're going to pipette up the organic phase and pipette it through this pipette that's packed column with this drying agent. So your liquid runs through the drying agent out the bottom of the pipette, and then use clean diethyl ether to run it through the pipette once all your product has gone through, just to wash the granulated sodium sulfate, and then leave your vial uncapped in a drawer, because that diethyl ether with a boiling point of 1 degree over room temperature will just evaporate extraordinarily quickly overnight, and you'll be left with nothing but product. So make sure that last tube is tared, because the next day you get your weight of your product. That's what you would do if you're in the actual lab, but you're not. So there's your sodium sulfate columns. Oh, and I just want to point out this weird looking thing right here. That's just something that goes on top of the reflux condenser, so that you're not heating a sealed system. This is just cotton, so it's not totally sealed. But in between these two cotton plugs here is calcium chloride beads. They're also an additional drying agent. So if any water vapor from the atmosphere tries to get into your system and screw with your reaction, calcium chloride will eat it right up. So this is more like a drying top tube. So it vents the hot vapors without allowing water to come in, like a semi-permeable membrane. And that's all there is to that. So there is something really important about this reaction. You're going to need to go over this. So the chemistry involved, I haven't asked you guys to do this before, but this report is worth 200 points. So if you want to get 200 points on this report, you're going to have to talk about this mechanism as well as the chemistry. I'm looking for everything we've done before, as well as a description of this mechanism. So I'll go through it with you guys here. First of all, we have an alcohol and sulfuric acid. So the sulfuric acid is acidic, and here's your acidic proton. And it's acidic because it's able to leave easily. So here we have our electronegative oxygen on the alcohol, and these lone pair of electrons are semi-strong, and this wants to leave. So the OH will grab that proton, and this will form its sulfate here. And here we'll get a positive ion charge on the oxygen. So here you're going to have your alkoxonium bisulfate. So here's your alkoxonium intermediate, and here's your carboxylic acid. So your alcohol has now attacked your acid and formed its active intermediate with the ion. So now the carboxylic acid has a carbonyl, the C double bond O. Now O is highly electronegative, and C is significantly less. And with the 2 pi bonds here, there's a lot of tension and energy between those 2 atoms. So the oxygen, and the carbon, even though these are organic bonds, they are going to, and they're shared electrons, they are going to be hogged majority-wise by the oxygen. So a slight concentration of these electrons are closer to the oxygen than the carbon, giving it a slight partial negative, and the carbon a slight partial positive. So this partial negative on the oxygen is able to attack this positively charged alkoxonium ion And now that electrons have left this oxygen to attack that, this partially positive carbon is even more positive. So electrons from this oxygen come down because it's trying to stabilize that central carbon there. So here you're left with another intermediate. And then you have some electrons bouncing around to try and find the most stable configuration, which you end up with over here. And then moving forward, you're going to have an additional equivalent of alcohol, which will attack onto this unstable intermediate here. All right, this is a gem diol. And remember, before when we were talking about alkenes, vicinal is when you have a carbon next to another carbon, two adjacent carbons, and they both have OHs. So this is an OH and this is an OH. So you would say these OHs are vicinal to another. Now, if you have one singular carbon and you have both those OHs coming off the same carbon, then they're geminal to one another. So two adjacent carbons, same substituent, vicinal. One carbon, same substituent, geminal. So these are di, because there's two of them, ols, because they're alcohols. So diol. And since it's geminal, we call them gem diol. So it's a gem diol. So this gem diol is unstable because it has this positive charge in the center on carbon here. So it's attacked by the alcohol here, which forms this intermediate. And through a series of other steps between the alcohol and the alkoxonium ion that was formed, you'll end up with your tetrahedral intermediate. And finally, once you have your tetrahedral intermediate, which is essentially just what we just spoke about, the diol, except one of them here is drawn as the ether, and one of them here is the hyperhydrogenated oxygen, we could call it. So with these electron transfers, we're going to see this single bond turn back into a double bond, and we're going to see this OH2 leave as water. So water is getting evacuated. So then we're going to have our C double bond O right here, and our C single bond O, single bond R here. So what is that? An ester. So water is leaving, and a double bond O and a single bond O are forming. So an ester is forming, and water is leaving. And that's exactly what we see, and that's exactly what Fischer esterification is. And here, up in the top right, Zach has very kindly given you guys a step-by-step for the electron transfers, the intermediates involved, and et cetera for the Fischer esterification. But finally, you're going to end up with your carboxylate ester and your hydronium ion, which is really just water. No ions are formed as byproducts because we know ions are unstable. This is just water, and water at equilibrium will have a certain degree of hydroxide and hydronium ions in it, just because of equilibrium, you know? So hydronium is a byproduct, but in an aqueous solution, it'll quickly equilibrate. So I want you guys to speak about the mechanism for me, okay? I'm gonna need to see that in order for you guys to get full credit on this report. Right here, as I said before, 200 points. The chemistry involved. Now, data and calculations, etc. That's just gonna be calculating your theoretical yield versus your actual yield, your experimental yield. Real quick, I'll give you a value. Here I posted, see what values he gave you guys. I'll give you guys my own values. Zach did a nice job putting these videos together. Yeah. Yep. Sick. Smells like bananas, guys. So, or maybe it just smells like bananas to him and it's not actually the scent of bananas. All right, sorry. Maybe he didn't even give you guys, doesn't even look like he gave you guys values here. He literally didn't. Okay, guys. So just looking at this first page here and ignoring Zach, You guys are expecting about 1.09 milliliters of your liquid ester product. I would like you guys to do the calculations and give me theoretical yields, the mass, the moles, everything. If you guys actually isolated, let's go with 0.79 milliliters. I'll include that in the email. So you have 0.79 milliliters of your ester final product. Good luck on the calculations. Remember, this is worth 200 points, and I need to see all of this mechanism. What else? So explanation of the reaction. Maybe talk a little tiny bit about Emil Fischer, because he's a very important guy. And this mechanism. And as always, talk about the chemistry involved, what Fischer esterification is, what the process was, why you did things you did in the experiment. Focus on this mechanism. Mechanisms tend to bite a lot of people on exams, and they're worth a lot of points, like 20 points, 25 sometimes. So, you know, good to study it, especially these long ones. You could make an entire page of an exam, like one question, and it's a mechanism question, and it's something like this, or maybe twice as long for a single reaction. Like, it's a simple reaction, but he wants every step, and he's very, very tedious about it. I don't know what it's going to be like online this year. Maybe it'll be easier, but we'll see. Study your mechanisms. All right, guys, I think that's it. So I guess I will respond to your emails and talk to you soon. Good luck, guys.